Hello. Okay. I think we can start our class today. So today we will go to the next module. We call this detect the interest point in the image. So first we have to define what is the interest point, right? So let's imagine. Okay. I will show another. Okay. I will show you the. Explain to you what the interest point first. So example in frame one, and this is frame two, and frame one example. This is the image, our image, right? And inside we have example rectangular, and this is the frame two, right? And frame two is in the frame two, the rectangular already rotates an angle like this. Okay, an angle like this. Okay, so what is the interest point? Example, I click point. Example here on the first image, on the first frame. So can you find exactly where is it in the second frame? Can you find it? No, you cannot find. You just approximate. Okay, maybe it's appear here, appear here, or appear here. So that means this point is not the interest point. Okay. So example, I click on the corner of this one. The corner of this one. So in the frame tool, can you click on exactly the corresponding point? Yeah, of course, right? I can click here, right? Can click here. So so that means this one is the interest point. Okay, so this is the definition of the interest point. So the interest point is the point that you can easily how to say identify it in the next frame image. Okay, so this is the definition of the interest point. Okay. So in here, right? In here, example, they define that there is an interest point. Example is the corner at the roof here, right? At the roof here, and in the second image, they can find the similar point, right? The corresponding point at the touchy, right? Touchy. Okay. And in to detect the interest point, there are many kind of the interest point. So one of the interest point is the corner. Is the corner. So we have an equation. We algorithm. We call this is the Harris corner detection. So what is the corner? What is corner? So the corner is some kind like this one. Here you can see that, right? When you go on this direction and then you change the direction suddenly. So when you change the direction suddenly, so it will create an interest point. So this is the corner point. Here example similar. This is also the corner point. Example, you have the rectangular, right? So what is the corner? This one, right? So you change the direction, right? Suddenly, right? You change the direction suddenly. So this one is the point, corner point. Okay. So but in the image, so how to detect it, right? How to autonomous detect it, right? So we will go to the algorithm Harris detector. Okay, so let's see. Example, we have an image, and we have a feature like this, right? A feature, two line like this, right? So like this. Okay, so let's imagine that if we have a rectangular inside the image, inside this image, right? And I surf on this position, on this position. So this position, right? When I surf on the U direction or V direction, right? So when I surf on the flat, on the flat surface, so that means the intensity does not change anything. The intensity does not change anything. Okay. So when I surf on the edge like this, right? On the edge like this. So when I surf, right? When I surf it, and when I surf, when the position of the rectangular is at this position, right? And when I surf on the U direction, so when I surf on this U direction, it still don't have any change in intensity of the image. But when I surf on the U direction, V direction, right? V direction. So here you can see that the intensities in the V direction will change. So that means from this mark, because when I surf, I just recognize that the intensity in the Y direction, in the V direction change. So I know that, okay, I'm surfing on the line, on the line. And in the case 3, example, I'm is on this position, right? When I surf on any direction, the intensity inside the rectangular will change, right? Will change. So when I change on U or V direction, the intensity will change. So I know that I'm at the corner. I'm at the corner. So this is the principle working of the corner detection. This is the principle working. Okay. So from the principle working, so we will have the mathematics to perform the principle working, right? So this is the mathematics. So let's imagine that we have a rectangular, right? Rectangular, and the frame one, and this one is the frame two. Okay. So if all the point here, example, this one have the size example 5, and this is 5, right? So inside this one, inside the rectangular, we have 25 point, right? 25 point. And here, example, I surf U and V. Example, 1 pixel, like this, right? And I have 25 pixel, right? 25 pixel inside the new rectangular, right? Rectangular. So I will compare the intensity of all 25 pixel, all 25 pixel, and all new 25 pixel. And then I will calculate it, and then I will determine, oh, is it changing? And then I will determine this is the corner or not. Okay. So this is the mathematics of the equation here. This is the intensity of this rectangular, and this is the intensity of this rectangular. Okay. But to divide the intensity of a point, we will have the something like Taylor series. So the intensity of a point, the function of at the position x will equal to this one plus this one. Okay. So this one will become this one. Okay. And then I take the error. Because we have to calculate all 25 points inside, right? So we have a sigma here. Okay. sigma here, and then minus, right, correspondent. Example, first point here, first point here, second point here, second point here, right, correspondent. Okay, so we minus, right, and then we do the square. We do the square. So from this one we have this one. Okay, and this matrix is the one we have to concentrate on. Okay, we have to concentrate on. Okay, so from this matrix, we can determine that is the corner or not by calculate the lambda. Okay, private vector. Okay, and private value. Do you still remember? Private value lambda, because this one is the matrix 2 by 2, so we will have two lambda 1 and lambda 2. Okay, so based on the lambda here, yeah, we will determine this is the corner or not. So let's see. And okay, so this is the procedure to perform the high-risk corner detection. The procedure. Okay, by how to say, perform the mathematics, we have this equation. So what is the ix here? Ix is the derivative of the pixel. So this is the, to obtain this one, this is the, we do the Sobel filter. On x direction, and then iy here is the Sobel in y direction, right? And then we multiply it, squared, and then we put it in this matrix. And from this one we calculate the number r here, the r equation here. Okay, what is r equation? This one will determine if it's a bigger than a rest hole, So this is the corner. So what is this equation? You calculate the determinant of the matrix, right? And minus k and 3m square. So what is 3m here? So 3m will equal to lambda 1 plus lambda 2. Okay, and that will equal to lambda 1 and lambda 2. Okay, lambda 1 and lambda 2. Okay, so in Harris, to calculate this equation, dash and tray, right? We have to calculate the lambda 1 and lambda 2 of this matrix, right? But we have another method to calculate the dash, right, and the tray without using lambda. So the determinant of this matrix is very easy, right? Just like ix square, right? Multiply iy square, right? And minus, right? ix iy square, right? So this is the determinant. Okay, determinant. So and how about the tray? M. So by the calculations, right? Example, we have the matrix A, and this by calculation the lambda, the eigenvalue, we have the lambda 1 and lambda 3 here, right? They prove that the tray of the matrix will equal to the sum of this one, the sum of this number, the sum of the diagonal number. here they prove, right? The lambda, the eigenvalue of this matrix is 2, 2, 4, right? And multiply it is equal A, right? But if we plus the diagonal value here, right? So we will also have A. So it's equal. It's equal. Okay. So let's summarize the algorithm. Okay. So this is the algorithm. Okay. First, we have the matrix. We have the matrix or image, right? And then we calculate Ix and Iy here is we do the Sobel filter. Sobel filter. Okay. And then we square it. We square it. After we do the Sobel filter, we have the matrix, right? We have the matrix. And then just square the value. Square the value here, square the value here, right? And then you have this one. And then you apply the Gaussian filter. Gaussian filter. On this matrix. On this matrix. And then after this step, you have this one, and this one, right? And then you calculate the R here, R here, R here, right? Okay, so let's go to the example for clearer. Let's go to the example. Please wait a moment, please. Okay, let's do it. And where is it? Okay, here. Okay, example, I give you this matrix, right? So the question A, find the interest point. Find the interest point on this image. So by watching on this image, where right, we know that the interest point must be this one, right? Must be this point, and this point, and this point, right? Right. This is the Harris, right? Harris corner detection, right? So this is the corner, right? So let's perform the Harris corner detection, whether it can find this point or not. Okay. So the first is what we do. Let's remember. Derivative, right? So that means we do the Sobel filter, right? We do the Sobel filter. Okay. So to do the Sobel filter, we will. This one is the Sobel kernel, right? The Sobel kernel for phi and phi. But in your exercise or your problem, you just use 3 by 3 is okay, no problem. Okay. So this one is just the kernel of the Sobel, right? Kernel of the Sobel. So we do the filter, right? So we do the convolution, right? We apply, right? We serve this kernel on this image, right? And then when we serve, and then we have this matrix, Ix, Iy here, right? Iy. And then what we do next? We square up the derivative, right? Square up it. So what is square? Here, square, that means, example, we have this number. And then we square this number. We square this number. And then we have this one. We have this one. Okay. So we square each position on the matrix. And then we have the Ix square, I square, Ix, right? Xy, right? And then what we do next? What we do next? Apply the Gaussian filter, right? Apply the Gaussian filter. So we establish the Gaussian kernel, right? Gaussian kernel. And then we apply convolution, right? Convolution, this one on this image, right? On this image, on the Ix square here, right? X square here. And after we convolution, we have the matrix S square here. You see the after convolution with the Gaussian filter. Gaussian filter. S. And this one, XV here is this one, okay? And then what we do next? What we do next? Okay, we use a matrix 3 by 3, serve on the result image here. Serve on the result image here. Example, this one. We serve on this one. Okay, we serve this one. We serve here. We serve here, right? When we serve on the this one, on this one, we calculate what? Sigma, right? Sigma. So that means we sum all the value inside this one, right? And this is xy square here, right? Xy square here. And then we sum this one, right? And then we sum this one, right? We sum this one. We sum this one. And then we put it in the matrix. Example, when we square all the value here, we have this value, and then this value, and then this value, and then we put it in the matrix 2 by 2 here, right? Matrix 2 by 2. So this is the matrix 2 by 2 here. This one. This is the matrix 2 by 2. Matrix 2 by 2 here, okay? And then what we do next? We do the Harris, right? Harris calculation, right? And then what we do? What we do? After we have this one, right? After we have this one, so what we do? Calculate the eigenvalue of this matrix, right? Or we calculate the R, right? R here, right? The R. So the R here is equal to the determinant of this matrix, right? And then minus K multiplied 3, right? Square. The number K here is we choose 0.06. Just choose this one, okay? The optimal value. And then after this one, this step, we calculate the first point is this number. And then we put it on the matrix. This one is this one, okay? This one. And then what we do next? Serve, right? Move on next column, right? Move to the next column and then calculate exactly similar like this. Exactly R here. And then you have the second number, right? And then after you serve all the image, you have this number. You have the matrix here. The matrix here. And then from here, you normalize it to 0 and 255. 0 and 255. So when you normalize it, you have this matrix. And then the next one, what we do? The next one is we do the rest hole. We do the rest hole. Okay. So this one, and we do the rest hole example. We choose the rest hole value is 251. 251. So this one is biggest. You can see biggest value. And then when you do the rest hole, you will have this number. Okay. So this is the result of the high-risk corner detections. Okay. Result. Okay. So do you have any questions on the performing of the high-risk detector? Okay, if you don't have any questions, we go to the next one. Okay. Okay, so the next one. To detect the corner, to detect the corner. To detect the corner, okay, to detect the corner. To detect the corner, we have another algorithm we call shitomashi. Shitomashi. Okay. To apply this algorithm, it is similar to Harris, up to calculate the R matrix, And then what is the shitomashi algorithm do? So in the shitomashi, you have to or you must calculate theta lambda 1 and lambda 2. So in this algorithm, you have to calculate the eigenvalue and then compare to find the mean value and then put it in the R matrix. And then put it in my R matrix. Okay, let's see. Okay, so example at this step we have this matrix, right? At this step we have this matrix, and then we will calculate the lambda, the eigenvalue of this one, the eigenvalue. So let's remember the eigenvalue of this one, right? So we calculate by minus lambda multiply and then multiply the diagonal, right? And then by solving this equation, we find the lambda 1 and lambda 2 here. So the R value of the shitomashi is the mean of this one. So when from this point, from this step, we calculate the R value is the mean, right? And then we have this value. So we put it in the first position, right? First position. And then what we do next, similar to Harris, just serve more, serve on the matrix, right? And then put it again in this one and then calculate another lambda. And then after you solve it, and then you have the matrix here. We have the matrix here. And then from this step, you normalize it. And then you have this one, this value. Okay. So from this one, right? When you do the rest hole, okay, you have another corner, this one, right? It should be this one, right? It should be, right? It should be, right? Okay. Should be. It should be this one, right? But they find the inner corner, okay? You will find the inner corner. So it's okay. Inner corner, it's okay. Okay. So because this is the algorithm, they find the inner corner. Okay. So this one is the shitomashi algorithm. Okay. So this is the algorithm we perform by hand. Okay. So in the OpenCV, very easy. You just apply the equation, the OpenCV function. Oh, where is it? Where is it? Okay, in the OpenCV function, you just apply this one, corner Harris, right? And the parameter is you input the source image, and then you have the result here, right? Block size is the kernel size, That means you define a kernel, the size of the window you serve on the image, right? In the previous example, I use the size 3 by 3 to serve it, right? And in this is case size here, case size is the Sobel, right? Sobel. So in previous example, I use 5 multiply, right? But you can use 3 by 3. It's okay. Okay. And double case here is we choose 0.06, right? Okay. And this one is default. You just leave it default. Okay. And if you apply this one, you have the result very let's say very easy, right? Just input this function, and then normalize it, and then you just display. You have the final result here. And then just scan one and row and column, and then display it, and then you have this one. Oh, you have this one. This is the result by using the corner Harris function of the OpenCV. Okay, and this one is another. This one is to program by do not use the OpenCV function. Don't use the OpenCV function. So what we do? First, we have the image, right? Image, and then we do the Sobel filter, right? Sobel filter. X and Y here, right? Sobel filter. And then what we do? Multiply ix square, I square, and ixy, right? And then what we do? Gaussian filter on this image, right? Gaussian filter, right? And then after this step, what we do? Calculate the R matrix, right? R matrix. And then what we do? Just go to the R matrix and then scan row and column, and then do the rational. And then if you do you program by hand, don't use the OpenCV function. So this is the result. So it's similar to using Harris corner of OpenCV. Okay. And how to and about the shitomashi function, you use this one. You use the function we call, this is the good feature to track. Where is it? Okay, here. You use this function. Good feature to track. Right. And then this one is the sort, right? And this is the result number of corner. And this is the maximum corner you want to detect. Example 100, right? Maximum, just maximum. Quality level, you just let it the quality level 0.01. This is the resolution. And the mean distance is you just let it 1. Okay, the default value, right? And the mass is the just let it default like this, right? Block size, this is the kernel, the Sobel kernel. Okay, and this one is if you want to use the Harris detector, you use this option. And if you want to use the shitomashi option, you just change this one to shitomashi. The K is similar, 0.06. And then after that, you will have the result. And this is the program of the matrix. And this is the Harris corner detections use OpenCV function. And then this is the shitomashi using good feature to track function. And you can see that it's similar to do by manual calculation, right? By manual calculation. Okay, so this is the interest point detections, especially the corner detections. Okay, so do you have any questions on this one? Okay, maybe after you have a look at the exercise, right? The exercise I already post on the e-learning for you. Okay. Okay, we go to the next one. And the next one is we do the tracking, motion tracking, or object tracking. Object tracking. Okay. So what is the object tracking? And we will apply the algorithm called Lucas-Kanade algorithm. So what is it? So what is it? So let's see. Example, this is the image, right? This is the image. See the image, right? And then I want to track, example, this car, right? So if I want to track this car, I will draw a rectangle surround it like this, right? So in the next frame, right? In the next frame, right? In the next frame, I want to find where is it, right? Where is the car, right? So that means where is the rectangular, right? On the next frame, right? Frame two, right? Frame two. Okay. So this is we call this is the tracking object motion. Okay. So how can we do it? How can we do it? So we will use the Lucas-Kanade algorithm. Okay, so the Lucas-Kanade algorithm is based on three assumptions: brightness, consistency, spatial coherence, and temporal persistence. So what is it? So what is it? Briefly speaking, we can say that condition. Three condition is to set that the changing of the object between two frames is so example frame one and frame two, right? The frame one, the changing is not too much. The changing is not too much. If it change too much, we cannot do the algorithm. Okay, let's see. Brightness consistency is that they assume that in the first frame one, sorry, frame one and frame two, right? The brightness here, the intensity here, change not too much. Change not too much. Okay, please wait a moment, please. Okay, we have a short break, 5 minutes. Okay, so short break, 5 minutes. Hello. Okay. Well, we continue. Okay. The first one is brightness, consistency. Okay. Okay. So that means summarize. They say that the intensity of the first frame and the second frame, the total intensity not change too much. Not change too much. Okay. And the spatial coherent, that means it's the that means the first frame and the second frame, the first frame and the second frame, they have to lie on the same surface, same surface. Okay. And the temporal persistence, what is it? That means the image must change gradually over time. That means, example, Taiwan, example, we have the two frame, right? Frame one and frame two, right? And in frame one, they have this position, and frame two, right? It just have change a little. Example, the moving U and V, very small. Normally just 1 pixel, 1 pixel, 1 pixel. Okay, so this is the condition. So because the moving of the object here, right, between two frames, just 1 pixel. So your camera, the speed have to be very fast to capture the image. Okay, you have to have the camera with the very high speed to capture the motion of the object. So this is the meaning of a temporal persistence. Okay. So so let's see. Example, we have this one. Example, we have in the first image. First image here, we have the 4 point, right? And 4 point will move on this direction, and direction, right? And then after the moving, we have this position, the new position of this point in the next frame. We can say this is frame one, and we can say this is frame two, right? So when we say this is the small motion, so that means this point and this point move not very far. So normally it, as I said before, just 1 pixel. Okay. So let's do the mathematics to calculate it. Example, I have the point, 1 point here, right? And the next one, it is the first frame, and it is the second frame, right? Second frame. Example, in the first frame, I have this point, and in the second frame, I have this point, right? So that means I want to know, okay, how much is already moving. So I have to calculate the U and V here. So this is the equation, right? So based on the brightness constancy, right? We just assume. So when we assume that the brightness consistency, that means the intensity of this point and the intensity of the new point here is similar. So it will equal. But as in the Harris corner, we already know that if it's changing like this, right? It's changing like this. We can do the Taylor series to the Taylor series, right? And when we do the Taylor series, we have this one. Okay. And this equation is rewrite on this one. This one. Rewrite on this one. Rewrite as this one. Right? Rewrite as this one. Sorry, this one. Rewrite as this one. Okay. So now what we do? Just let this one on go to the left hand side. This one. Minus. Okay. If we minus, so replace this one equal to this one, right? And then minus this one, right? Minus this one. And then changing the position here, we have this one. And then we have this equation. Finally, we have this one. Nearly zero here. Okay. So the purpose to derive this equation is to calculate u and v, right? U and v. But we just have one equation, right? One equation. How can we derive? How can we calculate u and v? No way, right? No way. So let's remember what we do in the object tracking. Previously, we have the car, right? The car, and then we have to draw a rectangular, right? Example, we have. So that means this one is 5, right? Example, the size is 5. So that means we have 25 points. Right? So that means we cannot track 1 point motion. We have to track at least 2 point motion. 2 points. Because this is the equation, right? The equation have two variables, u and v, right? We must have two points, right? So that means we have at least 2 points. So to detect an object, right? We draw a rectangular, and then example 5, we have 25 points. So if we have 25 points, so we will have 25 equations like this, right? If you find 5, we will have 25 equations, right? 25 equations. Point 1, right? Point 2, right? And then point 25, right? Inside the region, right? Inside the rectangular we draw, right? Inside the rectangular, right? And then we have this matrix, and this matrix. Can you solve this matrix to find u and v? Yeah, it's very easy. To solve it, very easy. Just do the transpose, right? This one will become matrix 1, right? And then we can calculate u and v here, right? U and v here, right? And in the image processing, right? To do this one, to do this transpose like this one, it will equal to this matrix. It's equal. So what is it here, right? This is the Sobel filter, right? In the previous example, we already calculate Ix, right? It is totally similar, right? And is it the matrix of the Harris corner? Yeah, this one. And then this one is this one, Ix and It. So what is It? This one, right? What is this one, right? This one and this one. So this one is It, right? It. So this one we derive more clearly is this one. The It is this one. Template minus current image. Okay. So that means what is it? The first image, right? And the second image, right? Just let this one and this one, example, we have 2 points, right? Just the intensity of this point, and this is the intensity of this point, right? Just minus this one, minus this one, this one, minus this one, right? And then multiply with Ix, and then do the sum, and then you can calculate U and V, right? And in here you can see that, as I said before, U and V, it is very small. Normally it is smaller than 1. Okay, smaller than 1. So when you calculate, the result of U and V must be iterate. Example, the point move 2 pixels, right? 2 pixels. So U and V, it will iterate step by step. Example, you calculate 0.25, something like this, and V equal to 0.01, something like this. In this case, right, 0.25, you will set it equal to 1. You see delta U here. And V here, 0.01, you can set it equal to 0. You see here. Okay. So just do iteration step by step, and then U and V will become 0. U and V, delta U and delta V will become 0. Okay. Okay, let's do the calculation example. Okay. Okay, this one. Example, I give you this one, right? This one. And you have this one, right? And you have this one. Okay. So okay, so let's do the calculation using Lucas Kanade. Okay. So example, we want to track this point and this point. Okay. So from this point, I draw a rectangular 3 by 3. 3 by 3. Okay. So let's do it. So the first one is we do the Sobel filter. So this is the filter. You can use the Sobel filter kernel here. Okay, no problem. You can use it, Sobel filter here. Okay, and then after you do the Sobel filter, and then you serve on the image, right? Convolution, right? And then you have this image. You have this one, and this is the Ix, and this is the Iy, right? And what we do next? Just square, right? Square. Ix square, and then I square, right? And then you have this one, and then what is it? What we do? Ixy, right? And then what we do? We have to put it in this matrix, right? So the next step is to calculate the sum of this one, right? The sum of this one, and the sum of this one, and the sum of this one, right? So to calculate the sum of this one, right, we just apply the kernel 5. This is it. This is the kernel. We apply on the image, and then we calculate the sum of all the point here, right? And then we have this one, and then we have Ix square, right? At first position, Ix square at the second position here, X square of the third position is here, right? And then you put this on the matrix. Sum Ix square, and then sum of I square, and then sum of Ix, and then we calculate the, what is it? What we next? We calculate the IT here, right? zxy minus eixy, right? So the next one is we want to calculate this one, right? And then when we minus, we have this one, it, right? And then ixt, right? Just multiply, right? Just multiply. Just multiply. Ixt, iyt, and then put it in the matrix. Put it in the matrix. Put it in the matrix. Put it in the matrix here, right? Put it in the matrix. And then you can calculate the u and v, right? You can calculate u and v. U and v. U and v. So after you calculate, you will have this number. This number. Okay, let me do the programming example for you. Okay, this one. Okay. This is the okay. This is the original image. Okay, so let me see. Okay, yeah. Okay, so first position and second position, right? So let's see. So I click and run it. Okay, in the first iteration, we have this one, 0.17 u equal to 0.17, and this one, right? So that means 0.17 here, you can set it is equal to 1. So that means it move on the right. It's move to the right 1 pixel. And v is very small here, you can set it 0. You can set it 0, okay? So assume, right, this one is move to the right 1 pixel, 255, right? Move to the 1, 255, right? Move to the 1, 255, right? And this one becomes 0, right? And this one 255, 0, 0, 0, okay? So it's already moved to the right 1 pixel, right? So let's do it again. So what happened? Okay. Okay. Now it's still move to the right 1 pixel again, right? And then v is still 0 because it's very small, just 0.06 is equal to 0, right? So we will move to the right again. 55, 255, right? And then 255, and then this one is 0, right? And this is become 255. One is 0, this one is 0, 1 is 0, okay. And then let's see what happened. Let's see what happened. Okay, here you can see. Now u direction is very small, 0.01. It's become 0, right? But now you can see v. V here is bigger, 0.14. So you can set it become 1, right? You can set it become 1. Okay, you can set it become 1. So from this example, you can see that it will go step by step, one iteration and one iteration, right? It cannot convert immediately. It cannot convert immediately. Okay. Example, I move to the right. I move to the right more. So what will happen? What will happen? So let's see. Okay, you can see here. You can see here. Minus 0.17. Okay, so that means I have to move to the left 1 pixel because this is minus, already minus. And how about the V direction? 0, right? So in the V direction, I don't need to move anymore. Okay, so this one. Okay, so this is the equation, right? This is the equation. So this is the algorithm, Lucas Kanade algorithm. Okay, so do you have any question on this one? So do you have any questions? Okay, so I think that after this class today, I think you have to watch the movie carefully again, okay, to understand more about the algorithm. Today we already studied 2 very important algorithms: Harris Corner, shitomashi, and Lucas Kanade. Okay, so do you have any more questions? Okay, if you don't have any more questions, we can dismiss the class now. Okay. Okay.
Thầy ơi, cho em hỏi là cái bài tập về nhà bài 2 còn tính tay không thầy ha?
Please wait a moment. Ý bạn hỏi là bài nào? Bài mới hay là bài cũ?
Dạ bài mới.
Okay, let me remember. Is it here? Is it this one? Yeah. You have to do it manually, right?
Yeah.
Yeah. Okay. Okay. Any more questions?
Thầy ơi, em hỏi bài sáng nay á thầy.
Bài sáng nay á hả?
Bài sáng nay cái bài 2 có cần phải làm tay không thầy? Bài 2 á
Bài sáng nay á hả? Là bài gì ta?
là ý là bài tập về nhà á thầy, bài tập về nhà mà bàn vào sáng nay á, cái bài 2 em không biết là có phải làm tay không?
Ủa sáng nay làm gì có bài tập về nhà ta?
Cái bài tập về nhà cho tuần này á thầy. Bài tập về
À,
nhà.
ủa mình mới trả lời bạn kia xong mà ta. Đây, bài số 2 nè, đúng không?
Không phải bài cũ á thầy, không phải bài đó.
À, bài cũ á hả? Ý hỏi là bài cũ á hả? Để mình coi. Bài cũ. Bạn đợi tí bài cũ để mình lật ra đó. Bài số 2 là tựa đề là gì ta?
Dạ. morphological operation 2 thầy.
Bài
Bài
số
tập 4.
2 không, bài số 2 không làm bằng tay ha, làm bằng tay sao nổi, làm trình thôi. Nhưng mà các bạn phải giải thích nha, phải giải thích nha.
Còn bài 1 thì cái answer boy thì chọn ở đâu cũng được đúng không thầy?
Answer boy các bạn chọn ở giữa ha, Ninh ha.
Cảm ơn.
Rồi. Có bạn nào mới hỏi mình là upload the VID last week hả? Ủa, VID nào mình cũng up hết mà.
Dạ thầy, video tuần trước thì chưa up lên nữa này. 8 tháng 10.
8 tháng 10. Ủa? Mình nhớ là mình up hết mà ta. 8 tháng 10.
Nó bị sót hết rồi, là thầy up sót.
Nhiều quá. Để mình coi coi. 8 tháng 10. 8 tháng 10 là mình... Ủa sao mình nhớ... Rồi ok, để mình kiểm tra lại nha, đợi mình tí nha. 8 tháng 10 hả? Chà. Mình up sót hả ta? Ủa chà chết. Đợi mình tí ơi. Mình không nhớ. Đâu rồi? 8 tháng 10 thì cái này nó sẽ đề là 7 tháng 10. Từ từ. Ôi trời nhiều quá rồi, giờ biết ở đâu đây ta, chết rồi. 8 tháng 10. Ủa giờ có cách nào để mà search trong cái này không ta, nó gửi cái đường link này về. Đợi mình tí nha. Lớp của các bạn sẽ có cái mã đặc biệt. Ok, đây. Ý các bạn là cái này phải không?
Dạ đúng rồi thầy.
Đúng rồi không?
Dạ đúng rồi.
Cái này mình chưa up hả?
Dạ.
Ok, vậy để mình up liền cho các bạn. Ok, sorry.
Dạ rồi, cảm ơn.
Ôi chà. Quá trời luôn. Rồi, nó đâu rồi? Rồi đây. Ok, để mình up cho các bạn. Nhiều quá. Ok, chưa up đúng không? Okay, sorry. I already uploaded, right? So you can go to the e-learning and then download it. Okay. Okay, so do you have any more questions? I both wrong position. I both mình post ngày 8 tháng 10 bên cái EXC các bạn. Lộn. Ok, mình lộn mất. Nó 8 tháng 10 buổi sáng. Còn 8 tháng 10 buổi chiều. Ok, 8 tháng 10 buổi chiều là kia đúng rồi. Ok, được rồi. Okay, so do you have any more questions? Okay, so if you don't have any more questions, we can dismiss the class now. Okay. Okay, so have a nice weekend. Okay.